This video covers two topics, conduction and induction, and electric fields. The movement of charge is limited by the substance a charge is trying to pass through. There are generally two types of substances. Conductors allow electrons to move readily through it. It's important that we recognize here that we're talking about electrons, because electrons are the ones that are going to be moving. Insulators restrict the movement of the electrons. So examples of conductors are copper wire, aluminum, and silver, generally metals. Insulators, like plastic sheath, glass, rubber, and wood, restrict the movement of the electrons. That's why wires are usually covered with plastic. There are basically two ways you can charge something, and when we say charge, that means we're adding or removing electrons. So if it has more electrons than protons, it is considered negatively charged. If it has a deficit of electrons, that means there are more protons than electrons, then it is positively charged. So these two ways are conduction and induction. Conduction happens through rubbing. Think of friction. It requires contact. Induction does not require contact. Think the definition of induce. It's to persuade. And we'll see examples of both of these. This picture shows an example of conduction. When you are charging an object through conduction, you are literally rubbing electrons off the surface of this object. So before this balloon is rubbed on the hair, both objects, the hair and the balloon, are considered neutral. They have the same amount of protons as they do electrons. Now, when they rub together, the hair is going to release electrons and the rubber is going to pick up those electrons. Afterwards, when you remove the balloon from the hair, you have the balloon that is now negatively charged, and your hair is left positively charged. So, as this balloon is brought up to some feathers, which are again electrically neutral, meaning the same number of protons as electrons, then what happens is the electrons move away from the surface that's closest to those electrons because of the situation we saw last time, that electrons or like charges repel and opposite charges attract. These are some situations we saw last year. Here you have rubber and fur that are being rubbed together. Again, before they are rubbed, the rubber and the fur are considered electrically neutral, the same number of protons as electrons. Afterwards, electrons are lost from the fur and the rubber gains those electrons. So now the rubber has a negative charge and the fur has a positive charge. When glass and asbestos are rubbed together, then glass is what's left negatively charged and asbestos is what's left positively charged. Again, if something is left positively charged, it did not gain protons, but in fact, it lost electrons. When you have a piece of glass that's rubbed with the silk, afterwards, the glass is left positively charged. Again, it lost electrons. And the silk is left negatively charged. It gained electrons. Any charged object, whether positively charged or negatively charged, will have an attractive interaction with the neutral object, and we'll see several more examples of this in class. This situation is more common. Here we have a neutral sphere that has the same number of protons as it does electrons. In the second picture, we have a negative rod that's brought up to this neutral sphere. As it's brought closer to it, the negative electrons are going to move away from this object. And as you notice, the left side is going to be more positive than the right-hand side. The right-hand side is going to be considered more negative because it has an excess of negative charges. And the left side has an excess of positive charges. Let's say in this third picture that a ground is attached to it. What that means is it allows electrons to leave the sphere. It gives us a way out. For this fourth picture, you see that we have removed the ground and now we have less electrons than we began with. So, as we remove the rod, our sphere is left positively charged because it has more protons than it does electrons. In the first picture, you see two electrically neutral objects. they are in fact touching. When a negative object is brought up to part A or sphere A, the electrons move away from it because like charges repel. So it moves as far as B because it wants to get away as far away as possible. Afterwards, B is moved away from sphere A. So now they are no longer touching. What that means is that B is now left negatively charged and A is now left positively charged. This is an important situation dealing with an electroscope, which is a device that shows the presence of charge. The simplest version consists of a frame with a metal plate on top and two pieces of foil hang next to each other inside the frame. A charged rod is brought near the metal plate of the electroscope. So again, this metal plate and the foil leaves are all electrically neutral to begin with, same number of protons as electrons. And this negative rod is brought close to it. Again, as it's brought close to it, the negative charges are going to move as far away as possible. So then you're left with the situation on the right-hand side. The electrons, or the most of the electrons, are located at the bottom part of this electroscope. Because the electrons are distributed on both of these leaves, then they are both considered negatively charged. What that means is because they are both negatively charged, they in fact will repel. So you're going to actually see that these leaves, these pieces of metal, are going to move away from each other because they show that they have the same charge. Now the top part, the metal plate, is going to be left positively charged. It will have more protons than it does electrons. Now, last time we talked about electric forces. We're going to talk about where those forces come from in terms of electric fields. Now, we said last time that all charges exert forces on other charges. This is due to a field around them. So what we can do is we can actually calculate the strength of that field with this equation down at the bottom. This equation comes from dividing the force of two charges acting on one another divided by Q, a point charge. So E is going to represent our electric field, or the strength of the electric field. K is Coulomb's constant, which we saw last time, which is 9 times 10 to the 9th. Capital Q is just a charge. Sometimes we use Q1 and Q2. Sometimes we use capital Q and lowercase q. It's just to differentiate between the charges that we're talking about. In this case, capital Q is going to be considered the source charge. The charge is actually creating the field. And R is the distance from the source charge to a point. So what we can do is we can use this equation to determine the electric field strength at a certain point. The electric field vector E at a point in space is defined as the electric force F on a positive charge Q placed at that point divided by the test charge. All that means is that you are looking at the electric field strength as it affects a test charge. Okay? So every charge creates an electric field. We can determine the direction of that electric field by placing a positive test charge and seeing what direction it would go. The test charge only serves as a detector of the electric field. Yes, we know that if this test charge is placed there, it also exerts its own electric field, but we're going to only focus on the source charge for now. An easier way to describe what we just mentioned is rearranging the equation so that it looks like this. That the force on Q, which is our test charge, is equal to our test charge times the strength of the electric field. So if we know how strong something is, then we can determine how it's going to affect a charge, any charge that is placed at a particular point. It's helpful to think of this in terms of gravity. We know that gravity actually creates a gravitational field. And if we place a mass in that gravitational field, then what we can create is a gravitational force. So E is going to take the place of G, and Q will take the place of M. So the force that it experiences is the force of the source charge acting on the test charge. Now, this bottom part in orange is important, but we're going to see this a lot more in the next section. If the test charge is positive, the force is in the same direction as the electric field. So in this picture, this positive charge over here is my source charge. Q1 is my test charge. We know from our last video that two positive charges are going to repel each other. So it has a force acting in this direction. We now know that positive charges have electric fields that go away from the charge. So my electric field is also in this direction. So if the test charge is positive, the force and the electric field are in the same direction. If this test charge were negative, then we know that it would have an attractive force. So the force and the electric field will no longer be in the same direction. Now remember that an electric field is a vector. It's always in the direction that a positive test charge would move. That's why positive charges have electric fields that go away from the object, from the source, and negative charges have electric field lines that go towards it. So you can also think of the electric field as the amount of force per test charge. Now we said that electric fields are vectors, so multiple electric fields can be represented as a vector sum of those electric fields. Now remember that electric field has units of newtons per coulomb, as we saw in the E equals F over Q equation. In this example, we have an electron is placed at rest in an external field of 520 Newton per coulomb, and we're asked to calculate the speed of the electron after 48 ns. This is nanoseconds, which is 10 to the negative 9. Because an electron is placed in the field, the electron is our test charge, and the charge of an electron is 1.6 times 10 to the negative 19 coulombs. So our electric field is 520 newtons per coulomb. Our test charge is 1.6 times 10 to the negative 19 coulombs. And with this information, we can solve for the force. Now, if this is the only force acting on my object, we can multiply by Q, multiply by Q. If this is the only force acting on my object, then the net force is equal to mass times acceleration. So, our test charge, which is 1.6 times 10 to the negative 19, times my electric field, which is 520, just checking to make sure our units work out. We get a force of 8.32 times 10 to the negative 17 newtons. Again, this amount of force is equal to mass times acceleration, so we can use that information to help us solve for the acceleration. So F divided by M is now equal to A. So 8.32 times 10 to the negative 17 newtons over 9.11 times 10 to the negative 31, which is the mass of an electron. This is not something you have to memorize. You can just look it up from the constants table. And you get an acceleration of 9.13 times 10 to the 13 meters per second squared. Now, this only gives me acceleration. We're asked to calculate the speed. For that, we can use the time given to us in the problem, which is 48 times 10 to the negative 9 seconds. The fact that it started at an initial velocity of 0. We can calculate the final velocity using kinematics. So, V is equal to V naught plus AT. V naught cancels out, and we simply multiply our acceleration by our time. Which is 4.38 times 10 to the 6th power. In our last example, we have a negative 4 times 10 to the negative 12 Coulomb charge Q, which is placed at the origin. What is the magnitude and direction of the electric field produced by Q if a test charge were placed at x is equal to negative 0.2 meters? Well, if we have a negative source charge, then our electric field is towards our charge. Our electric field goes in this direction. So if we want to know what the magnitude of the electric field is, we can use our first equation, which is KQ over R squared. Remember that K is a constant, which is 9 times 10 to the 9th. Q is our source charge, and we're going to put it in as a positive value so that the direction of the electric field comes from our conceptual understanding. And here, it doesn't really matter that it's a negative because it does get squared either way. So you get an electric field strength of 0.9 Newton per Coulomb. So this is our electric field strength at 0.2 away from our source charge. Now, it did ask for magnitude and direction. Because this is a negative source charge, then we've already determined that our electric field is going to be moving to the right at this particular point.